Good afternoon, everybody, and welcome to Modern Vehicle Hazards in Parking Garages in Vehicle Carriers. And we have two presenters today. Our first presenter is Havard Bamer. Havard is a senior engineer at CSE and received a master's degree from the University of Maryland. During his 10 years of experience, he has worked on a range of complex fire modeling problems, both for commercial and for research purposes, including smoke control, sprinkler spray, nuclear plant hazard analysis, and gas dispersion modeling. And Michael Klassen has worked at CSE since its inception, serving as principal research engineer, and has over 20 years of experimental fire and combustion research experience.
We're going to go through our work from a research foundation project. We discuss some of our findings and general conclusions on this work. There you go. Yeah. That's kind of what we went through. This is a research foundation funded project, and generally to provide guidance for these three main committees here: sprinklers, parking structures, and immersion vessels, and also general information for NFPA for future research and guidance. Okay, so moving on. General summary of the project. We're going to look at modern vehicle, as the title says. So it's clear that vehicles since, especially the 70s, 80s, the vehicles have gotten bigger, both in size and in weight, and also increased use of plastic. The question we had is, how does this affect the fire hazard these vehicles present, specifically to enclosed parking in parking garages and also vehicle carriers, marine carriers, to see the pictures here. So try to quantify this a little bit. And the second part of the project was to apply the hazard we find, and how does that compare to the codes as they exist now, and what requirements are for open and enclosed parking structures, and what are knowledge gaps, and what kind of research do we need to do to fill those knowledge gaps, and in kind of what's most important, what do we need to know more about. So just to look at the vehicle fire problem, specifically in parking garages, not looking at the majority of car fires are along the highways after collisions and stuff, and that's not what we're talking about here. We're specifically looking in parking garages and in vessels that carry vehicles. So there are about 1,900 parking garage fires every year in the U.S. This is the last from 2014 to 2018, so it's recent data. There are only 20 injuries, and so as to clarify that these injuries are often people that are intimately involved with the fire in the vehicle, and there aren't many injuries of people around the parking garage. It's about $23 million in property damage, but that can be a lot higher for certain incidents, as we'll see later. And if we're looking at, there's a small minority of sprinkler parking garages, and we can look at those. There are about 6% of the incidents occur where there are sprinklers, and about 12 of them, the sprinklers are effective, and 12 cases, the fires are too small. So when the sprinklers operate, they appear to be effective. But like I said, this is a less than 2% of all parking garages have sprinklers. So just looking at some general smaller incidents, these are just some we've summarized from January for 2019, where there's a handful of cars involved, up to 17. There was the case in Newark. There's also a recent one that happened several this year, and one was 3,000 cars burned up in a parking lot in Florida, for instance. So there are a lot of fires involving parking vehicles. So these are actually small incidents where there aren't, it appears the fire department arrives, puts out 1, 2, or 3 cars, and there are no further damage. So we can look at some of the larger ones. I'm sure you've heard these, most of you. Liverpool in England in 2017, New Year's Eve, there was a large garage with about 1,500 vehicles parked in the garage. It was filled to capacity. There was an older Land Rover there that unattended. It ignited. It's not clear why. It says modify fuel system, but there's no more further data. The building ended up being demolished. This is a concrete structure. And this was a $25 million loss. And I remember 23 million is the average in the US for all parking garage fires. So this one vastly larger than the average. We found an interesting quote here from the investigation into the incident where the AHJ or code from 1968, which is built under, is that fire spread from one vehicle to another would not occur, and they expect the fire department to be on the scene within 3 to 4 minutes. So if you look at what actually happened in this fire, the CCTV cameras find that it took 13 minutes from when the smoke was first observed until anyone reported the fire. You can see in the pictures here, these are people who did not report the fire. A few minutes before, they were walking by. It's also somebody drove by, stopped next to the fire, and then drove off without calling 911. The fire department did arrive at 21 minutes after the fire started. So much shorter than the 3 to 4 minutes that was expected in the original 1968 codes that applied to this building. When the fire department arrived, they basically had to start trying to put out the fire from external. They could not enter the building, and there was fear of collapse. And they reported that every 30 seconds they saw another car go up in flames when they were trying to enter. Second one, kind of rather famous fire happened a few months ago in Norway at an airport parking garage. This one, there was an attended vehicle. It had been sitting for a few weeks. The family was on vacation. They got back to their car, started up, and the driver reported to have seen smoke coming from the engine compartment and then seeing fire. And then he, for some reason, exited the building before he called the fire department. I think he said it took about 8 minutes before he called, and then it took the fire department arrived at about 19 minutes after ignition. So this was similar size. About 1,300 vehicles were damaged, 400 of them were totaled. And as you can see in this photo, the building collapsed. The steel part, this was a 3-part building. The center one there is concrete. The one closest to the camera here is a steel structure, unprotected steel. So that was a pretty big collapse of that whole building. They say about 2 hours after the fire started. This building had been given a special dispensation to have a 10-minute fire resistance on the steel. It's not clear why. 15 minutes is the code requirement there. But as we saw, the fire department was about 10 minutes away, just driving there. So they again arrived a little bit later. This is estimated, as you see, to about $47 million in loss, which is not including having to shut down the airport for several days. So it's again another extremely large incident. So we can move on to the general breakdown of this problem. As we said earlier, vehicles are larger, wider, taller, and heavier. Sorry?
Sorry, it's just cutting out a little bit more. I don't know if it was your microphone maybe too close.
Okay. Let's try it over there. Is that?
Sounds good. Thank you.
Okay. Yeah, just let me know. Okay. Yeah, so we can look at larger vehicles. They have more plastics, like I said. This image just shows kind of a general types of plastics are all over the vehicles, externally. Bumpers, instrument panels, a lot of exterior panels. Vehicle stackers, which are becoming more popular to save space. That we see there a two vehicle high. That we also make them 3, 4, or more, both inside and outside. And again, just generally denser parking. Parking lots are getting smaller, and the vehicles are getting larger. So the result is the vehicles are parked closer together. So yeah, we're gonna go through the codes for parking garages in the US. We have NFPA 88A standard for parking structures. Which also the codes around the world are often similar to this one. We see a lot of the similar requirements. So the code breaks it down into open and enclosed parking structures. So an open parking structure is generally 20% of wall area is open, both internally and exterior, and also has to be on opposite sides to create an airflow through the building. So sprinklers and fire alarms are not required in open parking structures, so there's no requirement for that. And if it's non-combustible materials, you basically have unlimited height. If it's attached to other occupancy seats, there are some requirements for fire resistance, 2 hours generally, but no further requirements to notification or detection systems. So we have some enclosed parking structures, which are generally sprinklers are required if they're underground, if they're enclosed or within other occupancies. Sprinklers will be required. And the stack systems we discussed, they require per NFPA 13 is an extra hazard and requires sprinklers. Often in-rack systems are included there. So we can move on to marine vessels. There's a lot of codes here. Generally for US vessels is NFPA 301. But of course, there's a lot of international shipping, and then the International Maritime Organization has a document, Safety of Life at Sea, which has a chapter on fire protection. It was majorly revised in 2002, which in general came with stricter requirements after quite a few significant fires on ships in general. And depending on what kind of ship it is, there are requirements for separation, heat and smoke compartments, and for the vehicle carriers, it's generally required with sprinklers and other systems, for example, CO2 systems in enclosed spaces. There's the drainage requirements to ensure that sprinkler system don't cause listing of the ship and reduce stability. And crews have to be trained and have firefighting gear to fight the fire, since they're obviously far away from any assistance. How good the training is obviously depends on the resources of the shipping company, so that can vary. Okay, so we're going to move on to just generally looking at the vehicle fire hazards, how that breaks down. We have these 6 points. We look at some full-scale testing done on older and newer vehicles. We look at the plastic contents and how that affects the fire hazard. The employment of plastic fuel tanks, which is near universal at this point. We can look at alternative fuel vehicles real quickly, design parking structures, and also the marine vessels and how they are impacted. Okay, so we're looking at full-scale testing. It can be rather limited, since these are obviously expensive tests to do when you're burning one or more full vehicles. Often older vehicles are used, so that further complicates that. But just in general, we found that you can get what we call large fire, 7 megawatts and up for vehicles from any age group. We look back to the 70s up until now, and also the curb weight of the vehicle itself, they can yield rather large fires, even if they are smaller vehicles. We find sort of a cutoff at the mass loss percentage. This is just a general correlation. It's not a universal rule, but if you're below 16-17%, have a smaller fire. If you're above 17, which is where more of the vehicle is fully consumed, up to about 20-25 seems to be the upper limit. Then you get these larger fires. So the question is, does more plastic lead to greater mass loss and or faster spread of the fire? So this is a table showing some of these findings. So we have that cut off there. We can see the peak heat release rate is the one we've pointed out. Let's point this out here. Yeah, we have this cut off. We go from, this is sorted by mass loss percentage. This the last column. So we see you can have a vehicle fire that's as small as 1 to 2 megawatts, or up to 8, 9, or higher. And we see the years of the vehicles here on the left. We have some vehicles from the 70s, so this is only one test series, so it's rather limited, and the vehicle wasn't really fully consumed. And we have newer and older vehicles that give us these values of about 8 to 10 megawatts for, seems to be more the value for a fully consumed larger vehicle. So we just plotted some here. These are some of the fires where fire tests where we have that higher mass loss percentage. We would call a more fully consumed vehicle. Try to label the years here, line them up. But we can see there's a bit of a spread. We have the 2010s being faster and higher, but we also have some from the 80s or 90s, which are similar peak heat release rates. So it's difficult to draw any broad conclusions that newer vehicles are necessarily burn faster or with higher peak heat release rates. Much more important is how the test is set up, because there are, especially the ignition source and location, the vehicle can be ignited with an ignition source in the front seat, under the engine, in the engine, in the trunk, which has a very large impact on how the fire spreads and where you get the peak, and if you get a higher peak or not. Obviously, ventilation, windows open or closed. Some of the tests were done with the car windows closed, and the fire might not even break into the passenger compartment, and you get a much smaller fire. Whereas if you have the windows open, or if they break out, the fire generally grows to these larger sizes. And obviously the characteristics of the vehicle itself, how large is it, and what are the plastic contents, and how much combustible material is there. Also note that a lot of these were done under a hood, where you have all the gases from the vehicle going up into the hood, and you have much less radial feedback that'll speed up the fire, which obviously impact greatly the peak heat release rate. Some tests were done for tunnel fire research, where they test a vehicle in a tunnel and then they extract the gases at the end, which can give you something that's closer to a parking garage scenario. So just generally here, on car sizes, we're looking at, these are just some of the 2 most popular vehicles in the US for quite a while. Just generally, they've been, the Toyota Corolla has gotten wider. I really like the width here because, like I said, that dictates how close vehicles are together and how the fire will spread, which we'll see is pretty important. So yeah, the Corolla has gotten 20 centimeters wider and 400 kilograms heavier. The Ford F-150, not quite as much growth, but it's all gotten bigger. So then we move on to just the plastic use in the vehicles. We have these are data for the average U.S. light vehicle, which is generally passenger cars and personal vehicles, excluding larger trucks. So this is combined over 3 or so different sources, which provide the data. So we have some gaps, and we have some 5-year averages there for the older values. But generally, we see a trend up, both in the curb weight of the average vehicle, with some ups and downs. Probably came down there in around the oil crisis in the 70s, and then it got small in the 80s. I mean, growing since then. The weight of plastic has gone up, both in absolute numbers and as a percentage of total vehicle weight. So you see that it's not quite a doubling. I think it's about up by 70%. but in absolute values, it's about double, from 80 kilograms to 160. So yeah, we had a kind of a peak value there in 2009, and it's dropped down a little bit since then. It's not quite clear why. The curb weight has stayed pretty steady, but the plastic weight has gone down and up again in the 2010s. So we can note here is we see kind of like pretty sharp growth in plastic weight up in sharp growth here, and it's more or less steady here. So this is around 2008. Seems to be kind of a what we call a cutoff, where values before and we start to get quite different numbers for the vehicles. As we'll see later, using a vehicle for fire test from this time back here is going to be less and less similar to what a current vehicle looks like. So the plastics used, we have these three types, which is about 2/3 of all the plastic used in vehicles: polypropylene, polyurethane, and PVC, in that order. So they make up. So we have heated combustion here added for these. So obviously polypropylene is the highest, and the others a little lower. When we look at all the plastics used and we have a weighted average, we come out to about 30 kilojoules per gram of plastic. Obviously important to remember that the plastics can often replace non-combustible materials like metals. So once you add on this heated combustion, you obviously dramatically increase the potential fire energy in the vehicle. Though not always. There was some more wood in vehicles before, so it could be replacing that too. So here we have the same chart. We just replaced the plastic weight by the plastic energy, which just scales by the heated combustion. So we can see we have an increase here from about 2,500 megajoules up to almost 5,000 since the 70s. So that gives us this number here: 2,300 megajoules increase in plastic energy, which is a doubling of the potential energy from plastic in a fire. So for comparison, we have on the smaller test, we had about 3,300 megajoules from the total car fire in the 70s. Like I said, the curve is fairly steady, so it's more of an impact of the plastic increase. There's some general trends we've found. This is more from the plastic industry, looking at kind of future options for incorporating more plastic. We have body panels and windows, even including windshields and the side windows, looking at replacing those with plastic, which, as we see, will note here, will have an effect on the fire spread from one vehicle to the next, and also replacing other underhood systems with strong plastics, which will generally have the effect of increasing the size and duration of the fire. Plastic fuel tanks are already close to 100%, but we're going to expect to see a further increase there to being at 100%. So let's take a look at the general fire spread mechanisms in the vehicle parked in a confined space, under a ceiling, in a parking garage, in one of these marine vessels. We have direct radiation from one to the next, or a fire in one vehicle heats up the one next to it. We have radiation from the hot upper layer, and then obviously convection once the upper layer reaches the vehicle, especially in low ceiling situations. And we have bursting of that fuel tank and a pool of fuel running under the next vehicle, and the fire spreading along that path. We found some of the tests where they've looked at vehicles parked next to each other. They say the fire will initially heat up, especially the interior of the neighboring vehicle, and once the windows break, then the fire will jump into the cabin of the next vehicle. That's how it generally spreads. You need that period of heating heating up the vehicle. So here's a test we looked at. It was from the Building Research Establishment in the UK. Did some pretty extensive tests on a mock-up parking structure with some spread scenarios there, different setups. Here's one they used. We had the stars in car number 1 here on the right, and they found that it took 10 to 20 minutes for the fire spread to this vehicle next to it. Then they had an empty parking lot here, and then they had the third vehicle took 4 to 5 minutes before the fire jumped over there, over this gap in the spot. Yeah, like I said, you get about 1,000 Celsius ceiling jet, which will preheat the neighboring vehicles very quickly and increase the spread rate, and it goes up dramatically once you have that 2 large fires going. Obviously, this only goes in one direction. If you had an actual parking garage, you'd have vehicles on the right too. So you spread to 2 neighboring ones at the same time, and then the 2 next there again. So it would be more dramatic, and that's kind of like what we see is missing from some of this research, and that you don't have those scenarios because it's cheaper to even limit the number of cars you have to burn. Okay, so we're gonna. Sorry,
we're just experiencing some more. You're cutting out just intermittently there.
okay.
If you could just check your microphone icon in the bottom left-hand corner of the screen, you might be able to just readjust your audio.
Let me see what it says here. Let me try this here.
Let me switch microphones. Can you hear me better?
Yes, let's try that. Yeah, that sounds good. Thank you.
Let's stick with this one then. Okay. Yeah. So let's look at an actual fire spread scenario. This has happened just I believe a week or 2 ago. This was in China. This is an EV that started. It was charging, and the fire started. It looked like in the battery underneath. That's the different ignition, but so this footage came out. So we see the fire there in this on the EV. There's a truck parked next to it. After we don't have exact times here, but we see the fire spread to the wheel well around this around the wheel on this truck, also starting to ignite the tires. And in the last slide here, we have the tires full involved. The door handle is plastic, starts to burn. Eventually, you see burning on this mirror as well. And I believe the brakes fail on the truck and it rolls backwards. But the whole side starts to burn. All this takes about 2 minutes from start to finish here. Also see the charging cord for the EV is also actually pretty significant fuel source there. So there's another car next to this truck where we see, I didn't have room for the picture, but there we see that one starts to burn on the lights. The plastic lights on that vehicle starts to burn as well. So you see the fire jumps to the exterior of the vehicles via the plastic materials there. Another test that was part of the BRE testing was the stacker test, where they had the stacker system here. There's a car underneath. They do two different ones, one with sprinklers and one with no sprinklers. The one on the left is about 10 minutes in with no sprinklers, and you can see a pretty dramatic fire there with full engulfed the upper vehicle. Picture on the right is, like it says, 1 hour and 20 minutes, and this is with sprinklers both above and also in the rack of the stacker system. So the lower vehicle is fully involved, but the upper one does not catch fire. So yeah, let's the effect of this. We stick with the BRE test here. As I said, the NFPA 88A looks at the fire resistance of this building and using the ASTM E119 curve here on the left, which is temperature or per hour. Those are hours, the units there. And we'd see, yeah, after about a couple hours, you reach about 1,000, 1,100 C. This is results from the BRE test where we highlighted that 1100 Celsius curve, and we see that we reached that in about 5 minutes. Obviously, it drops down again, whereas the E119 is a steady curve where you have this constant heat exposure. But as you ignite, as you have more vehicles burning, you can have this temperature staying around that 1000 C. Can stay there for quite a while if you constantly have vehicles igniting. We can also see that the critical temperature for steel, generally around 550 Celsius, is also reached in about 4 minutes. And several of these thermocouples stay above that 550 C for quite a while, even in just one vehicle burning. So what are the effects of these temperatures at the ceiling? The two main issues we are concerned with would be spalling of concrete, which can have structural effects and also a fire spread effect. As we can see the picture on the left here, there's holes in the decking from spalling concrete. This is from the Liverpool, by the way, on the left, and Norway fire on the right. So yeah, we can then have fire spread through the floor and through the ceiling through these holes in the concrete. The critical temperature there can depend, but it's around 370 Celsius for the point of steam, where the water inside the concrete. This is obviously the temperature of the water inside the concrete. So it takes a while for the temperature gradient to reach that internal point. So when this occurs will depend highly on the density of the concrete and various other factors. You have to maintain above that for quite a while. It can take 20 minutes to hours, depending on a lot of factors. Steel, like I said, is about 550 is what's considered the steel temperature, is the critical temperature there. Again, you have to have sufficient temperature to heat the steel to that value, not just the air around it. But with unprotected steel, it can occur pretty quickly. And as we saw in Norway, it can lead to structural collapse of the whole building. Like I said, these values were seen in about 5 minutes. So at that point, you start to build towards that internal value. Okay, so we're going to move on to the next point was the plastic fuel tanks. Generally, about 80% of vehicles these days have plastic fuel tanks. It's slightly higher in Europe than in the US, where it's in Europe, I think it's about over 90, probably even higher at this point. They are generally made of high density polyethylene, which has a heat of combustion of almost 44 kilojoules per gram. And the average tank will be about 8 to 10 kilograms. So you get 350 megajoules or so, or up from the tank itself. So that is a rather significant fuel source in itself. So there's a UN ECE, which is a general kind of a consensus ruling for these plastic fuel tanks. They have a 2-minute fire resistance requirement. The test involves a pool fire underneath kind of the size of the tank. So it's simulating more or less a tank leaking and a pool fire starting underneath the tank itself. The tank is supposed to last 2 minutes before any fuel leaks out. So there was some tests done by Southwest Research Institute. That's the picture we see here on the right, where we see a tank that's being deformed and the fuel has started dripping out. They did a series of tests on fuel tanks in various conditions. Some were new, some were on used vehicles, and some they tested again after some exposure. But in general, they found failure in just before that 2 minutes or up to 4.5 to 5 minutes. So that's only one test series, but that's a data point telling us how long we can expect one of these tanks to last before we start to see fuel leaking out and potentially developing a pool underneath one vehicle, or if the fires jump from another vehicle, this is when the neighboring vehicle could start to leak fuel if it's burning underneath. So real quick look at alternative vehicles, specifically battery electric. This is where you have general lithium-ion battery and electric motor. It's a rechargeable battery vehicles as opposed to hybrids or other fuels. There's been quite a few tests done on this. Generally, we find that the peak heat release rate for an electric vehicle is lower than an equivalent internal combustion, the ICE vehicles. The curves are also more or less similar. There's no significant difference there. The fuel load of a burning lithium-ion battery is lower than the equivalent gasoline tank of the similar vehicle. So that makes sense from a theoretical and testing perspective. So we have this graph here. It can be a little hard to distinguish, but we have it shows two test series where there's the solid and the dotted lines. These are equivalent. The EV is the electric version of the same vehicles from the same manufacturer. So these are very similar vehicles, except for the propulsion system and fuel. We see here that the ICEs are higher peak heat release rate. The main differences are going to be how it burns rather than how hot. We have obviously it's been a few famous cases of thermal runaway in lithium-ion batteries, especially after mechanical impact or other damage. I know Tesla had some cases where it alleged that they ran over something and hit the battery underneath, and the vehicle started to burn. They installed a kind of protective a shield on their battery after that, but it can also be other collision scenarios. Obviously, in a parking garage, that is not a huge concern. The cars aren't really driving quickly, and there's few collisions. So it's going to be more once one of these EVs are impacted by a fire in another vehicle, the thermal runaway can occur and contribute to the spread. There's been issues where there's a very long reignition period. EVs catch fire, the fire department puts them out. Hours later, they keep reigniting. They often have to apply water for several hours to cool the battery down and stop this reigniting. And as we see in this picture here, there's a jet flame that can come out, and we saw a similar thing in the footage from the Chinese fire there, where the fire shoots out from the side of the vehicle, and you can imagine that if there was another car parked next to this one, it would have this jet flame impacting on it. And that's a concern for firefighters, and how they deal with that if they catch one of these in the parking garage. How do they put this out, and how do they move the vehicle, preventing it from igniting others? And can be a challenge from that perspective. We have a real quick look at hydrogen fuel cell vehicles. These have they have a lithium-ion battery and electric motor like an EV, but the main fuel is the hydrogen stored in a pressurized container, very well protected, since obviously hydrogen is quite dangerous. The rupture of that tank is the main concern there. Like I said, they are very, very, very strong, and there are pretty strict requirements to how you can store hydrogen in the vehicle. We see here in this photo comparing two vehicles that hydrogen car, once you have that rupture, the hydrogen will naturally go up and being very buoyant, and you can develop a jet flame, in this case going straight up. And you can imagine if there was a parking garage scenario, you would have then structural members above being exposed to this jet flame. Also other systems could be there if there's wiring and other stuff. So you can have the spread occurring that way, rather than with a gasoline fire where you generally get the fuel leak underneath and the burning on the ground underneath the vehicle. Currently, there are not much more than 10,000 of these vehicles half of them in the US, and there are a few refueling stations, mostly on a test basis around California. Toyota has one, they have a map, and there's nothing outside of California. So considering these are still in the research stage and very limited use, we didn't focus more on them rather than just highlighting some of these issues that then FPA and the fire protection community in general need to keep an eye on, and perhaps do more study as if these become more popular and start to show up. So when we look at parking structures in general, there's a lot of lacking hard data on evolution of parking garages. We have a lot of commentary from the industry and construction industry on various issues, but without specific hard data. But we have some of these general trends is that, as we mentioned earlier, the parking is getting denser as property values go up and the space is becoming more valuable. Parking on slopes and also integration into other buildings. A lot of trying to prevent sprawl. There's a lot of integration. We have a parking garage, a shop, and an apartment all in the same building. That will obviously have an impact on how the garage is designed. For example, if you have a parking garage on the same level as a store or an apartment, you will have height limitations as you try to match the ceiling heights throughout the building. And you can have very low ceiling parking garages, for instance. And again, there's the stacker systems increasingly being used to save space. So the issues we're looking at here, first is accessibility for firefighters, especially getting trucks in through these buildings can be a challenge. Especially US fire trucks are generally larger than Europe and other places, so they can have an even harder time getting through some of these narrow, low ceilings, small turn radius. So that can be a problem. And generally, as the vehicles are parked close together, we have the issue of fire spread, where running fuel down the slopes or even dropping down from one floor to the next, parking denser, and shielded fires as vehicles are stacked on top of each other. And as they get narrower, we get issues of venting of the hot gases. When you have the so-called open parking structure, if you have it very, very narrow, very densely packed, you can have quite reduced airflow through the garage. Okay, yeah, as I said a few times, parking spots are getting narrower and cars are getting wider. Yeah, we get the lower ceilings, which will lead to higher ceiling temperatures, which can on one hand lead to potentially faster fire spread from one vehicle to the next. But also if you have sprinklers in those spaces, then you can have a higher chance of triggering the sprinklers earlier. We highlighted two points here too that's been brought up. There's some talk of fuel stations in garages. Again, it's not a major issue yet, but something to keep eye on. This would be fall under NFPA 30A. And the second is fuel tanks, kind of linked to that, which also is kind of being discussed, but not widely adopted yet. But again, something to keep an eye on there. Okay, so we're going to switch over a little bit now to vessels, marine carriers, ro-ro vessels. If you don't know what that just means roll on, roll off. That the cars drive on, basically drive on and drive off down their own power, as opposed to being lifted on in containers or similar. So there's generally two types. You have the passenger ferries, like the one shown on top here. We can have from 100 to 500 vehicles. I think 500 is what's supposed to be the largest one in existence. So that's your upper limit. Couple thousand passenger or more. And And the crew, a large crew, which will be trained in evacuating passengers and getting them to safe places within the ship that are protected from the fire, and like I said, sprinkler systems, and large strict requirements for compartmentation of passenger versus cargo and vehicles. The second type is the pure vehicle transportation, the one on the bottom there, which is just the cram in as many cars as they can to transport them from, across the oceans. You can have as many as 5,000 vehicles or more inside one of these, and it's all cargo, so you can have a crew of maybe 25, maybe even fewer. Have some training in evacuating the ship and trying to save the cargo, save the ship, and evacuating if necessary. So yeah, go back to the codes for these marine vessels. We're looking at the IMO code for international, and then FPA and 46 CFR, which for vessels in US waters. The IMO is also enforced internationally in that if a vessel goes from one country, it's flagged in one country, it travels between two other countries, any of those countries can inspect and enforce the SOLAS codes. So it's not just at the country where you're flagged. So it can always be. So if somebody travels to the US, for instance, you have to follow those requirements as well. The protection systems are going to depend a lot on the fuel load and also on whether or not you have passengers. In general, now you have CO2 or another inert gas in the sealed vehicle spaces, and sprinklers in other places, or possibly foam systems. Again, you have detection notification systems everywhere, and crew are somewhat provided with equipment and training. But you got to highlight that they are marine crew. They are not professional firefighters. So you can expect them to fight a very severe fire. And obviously the issue of if you are in the middle of Atlantic, there are professional assistance from other firefighters is basically non-existent. We have two cases here, happened in the last 5 years now. Two fires aboard these vessels, the MV Honor in 2017. I believe it's on the English Channel. It was not far out of port. A fire started. I think it was allegedly in a faulty solenoid in the steering on one of the vehicles as a normal passenger car being transported. The crew got an alert. They put on the firefighting gear. They tried to enter space and cool down the bulkheads. They're unable to enter. They evacuated everyone and set off a CO2 system, which eventually put the fire out. The vessel was able to return more or less unharmed to port. So there was about $700,000 in damages per the official investigation, which is a significant number, but it's much less than if all the cargo and or the ship had been lost. So it's kind of be expected when you have these large open decks where a very large number of vehicles are stored in one space. If you have a fire, it's gonna spread and it's gonna damage a lot of the cargo. MV Courage was 2015, was kind of a similar scenario. Smaller vessel. I believe the Honor had several thousand vehicles. The Courage, about 600 vehicles. And again, they could not control the fire with hand lines, and they put out the CO2 system and put out the fire, and the vessel was saved. Okay, so we can go into a quick summary of what we looked at before we move on to the second part. Like I said, parking garage fires are relatively rare. Injuries are even more rare, and fatalities are almost non-existent. So from a public safety, it's relatively low priority. There's the potential for extremely large economic losses. Open parking garages is where you see that sprinklers or alarms are not required, so you are solely dependent on the fire department to put out the fire. And we have some issues of parking garages getting denser and larger, also integrated into other occupancies. So you have a proximity to potentially residential or commercial right next to the parking garage. Here's an interesting picture. I think this was noted in that table. This is a New York Airport fire where 17 vehicles burned up. I think this is the roof of the parking garage. Battery EVs, those fires are no larger than similar size internal combustion engines. We have the different burning characteristics to deal with, and the requirements of putting water on the battery potentially for hours. As you see here in this photo, this is a training exercise where they jack up the car to cool down the battery underneath. Hydrogen electric vehicles are could be a concern, but are so far of very limited use. And plastic fuel tanks are more or less universal at this point. So looking at the data on the vehicles, we've highlighted here on top that older vehicles should not be used for design of parking garages or for regulation, designing codes, basically. We put the number here at the 2000s, maybe 2008 is where we see kind of that peak in plastic content and curb weight, and it's been more or less flat since then. So 2010, it should be a cutoff. If using a vehicle older than that, you run the risk of not accounting for the plastic content and the potential spread between vehicles. We had the doubling of chemical energy from plastic since the 70s, and you can expect an 8 megawatt fire from pretty much any vehicle if the conditions are right. You can have spread from one vehicle to a neighboring vehicle in about 10 minutes. Could occur. This kind of we just went over marine vehicle carriers. There are very strict safety requirements which are enforced around the globe. Sprinklers, inert gas systems, and the crew will all contribute to try to put out these fires. And as we saw, the 2 recent incidents and also a broader study done by DNB, where they looked at general trends. They found that when systems are operational and the codes are followed, the vessel is generally saved and the fire is put out. So it's more of a compliance issue and enforcing of the code more so than the code being lacking. The systems have proven to be able to put out a modern vehicle fire. Okay, so we come to the kind of second part where we apply these things we found regarding the vehicles, and we're going to look at how is the current design criteria and current codes able to deal with these issues. Like we said, we have injuries to people are very rare, and usually people intimate with the fire in some way. Generally, this is kind of obvious. People in parking garages are usually awake. There are not many of them at one time, and people are spread out and generally leave as soon as they park their car or get in their car. But on the other hand, we have the potential for very significant property losses. We have $23 million in the US annually on average. But then we have those other outlier cases, which were not in the US, so not included there. The Echo Arena in Liverpool at 25 million, and the Stavanger Airport in Norway of 47 plus. The thing we find is that there's little leeway between a small and a large fire, meaning there are many factors that can tip from a single car or maybe 2 vehicles, which the fire department can very easily put out. But that fire, if that fire is allowed to burn for just a little bit longer or spread to another vehicle, it can jump to several more vehicles and be out of control very quickly. And the fire department will usually have to just evacuate the area and give up fighting it. So that balance between a fire that barely registers because it's a single vehicle, or one that spreads to potentially hundreds or thousands of vehicles, can be very small. And especially in these very large, dense parking garages. The one you see on the right there is, I would say, extremely dense. It's a lifter system where you have, I guess, a very, very tall car stacker there. Okay, so let's say the focus here is going to be on property protection, and how to potentially prevent these large fires and the outsized property losses more so than personal injuries. So yeah, we're gonna look at first the enclosed parking garages, that being the most where detection or sprinklers are required. I think in general sprinklers are employed in these cases. So as we've seen from the BRE testing and in general from statistical data, that the sprinklers are able to control at least a modern vehicle fire, including in the stacker systems. Since the car can provide a significant shielded fire, the sprinklers are not always able to put out the fire, but that's just a factor of controlling it in the igniting vehicle and also cooling off the vehicles next to it. It will give the fire department time to respond and prevent that out of control fire. The issue we see here is more about less ideal configurations of cars or fire scenarios where we have questions whether sprinklers could be overpowered. We haven't seen any evidence of that, but we haven't seen any. The testing is usually done in a pretty optimal setting where you have sprinklers distributed over the vehicle. So some issues to look at there might be, some of these less ideal configurations where you have a car parked in a corner or at the edge of the spray radius of a sprinkler or between sprinklers or something like that. That's where you could have issues, and something you might need to look at. And also, even if you have a sprinkler, you have significant smoke spread, and you have these integrated buildings. How can that impact occupants in nearby? And lastly, there, as the photo shows, is how can the fire department access some of these larger, denser parking garages? This was a case where, the fire truck fell through the floor because it was too heavy and got stuck there. It wasn't a fire incident, so it wasn't a big issue. It had to be lifted out, but that could be an issue, and just getting the fire trucks inside at all. You can have a 3 or 4 or 5 story building to get through. It can add a lot of time to the response time for the fire department. So next is the open parking garages. Obviously, as we said, detection or extinguishment is not required there. So that any fire there is going to be reliant on the fire department showing up on time to put out the fire before it can reach that critical spread and overpowered fire department. We have the issues, as you have in any outdoor setting, of the environmental exposure. Dust and wind and particles will hinder generally your optical smoke alarms, and freezing temperatures impacting sprinklers, etc. Increasing the cost of the maintenance to any system put there. And obviously, if you go from no system required to adding sprinklers or system, you add cost to what is generally a pretty low margin parking industry. Like we said, you're relying on the fire department, and the BRE testing found potentially 10 minutes to spread from one vehicle to the next. And like we said, if you're parked in the middle, then you're jumping from 1 to 3 cars after 10 minutes. And NFPA 1710, which I put the full name of it on the bottom here, sets in a criteria of about 5 minutes for one fire truck to arrive and be ready. That's after being alerted. So you also, how long it takes to detect and notify the fire department would add to that. A survey of some fire departments found that about a third of them could not meet this criteria. And as we saw in both Liverpool and Norway, it took 10 minutes before the fire department were even alerted, and then it took them another 10 minutes to get there. Yeah, so let's move on to where we look at some possible options for addressing these hazards. These are not exhaustive. This is more of a kind of looking at what's possible. Step one obviously would be to have some sort of detection system in an open parking garage, so that the fire can be detected and the fire department be alerted quicker, rather than just having occupants or eyewitnesses walking by and seeing the fire and hopefully calling the fire department, which, as we saw, many of them will not. The main issue is the dust and exhaust. For an optical alarm will be a severe problem. There'll be a lot of false alarms, or you have to set sensitivity low, and then they don't detect the fire at all. And not to mention the wind. If you have any wind or a strong wind, will blow the smoke out of the building potentially before it activates the detectors at all. Some options could be a video system shown here, where you don't have the issues of the wind, at least blowing the smoke away. Potentially heat detector systems. Spot type heat detectors will have the issue again of if the wind blows the smoke out too quickly, they will not activate. So that's still an issue there. There's also some more cutting edge system where you have a so-called smart detectors, multi-signal detectors, where you could have several detectors that interprets the signals through a computer, an algorithm that looks at not just what is the signal saying right now, but what is the over time value, and can then learn and interpret what is the false alarm and what is an actual fire. So second point, if not just detecting the fire, but also automatic extinguishment of the fire in open parking garages. We have the environmental issues here. Again, the wind effects on activation of overhead sprinklers, and also freezing, which is kind of common in all outdoor settings where sprinklers are used, also attics and places like that. So it's nothing new. They're putting this off in a dry pipe system, seen here, which will obviously avoid the freezing issue. It's a pretty simple system. The cost is increased obviously over no sprinkler system, but it's not a prohibitive cost there. The main issue remains of your spot type activation. You have to have the heat reach the sprinkler head and for long enough to activate it and apply the water to hopefully the right vehicle. I think I forgot to mention the Stavanger Airport fire. The wind was reported to be 35 miles an hour at that location, which is a pretty significant wind going through that garage. So we haven't really seen anyone look at what is the effect on detection and activation of sprinklers in that scenario, with such a significant wind. The second point here is so-called electronic sprinklers, which are connected to detector. You still have somewhat of an issue of getting the smoke to the right detector, but you can have a different sensitivity. You can also integrate this with a smart system where you look at several detectors, and this will have the multi-signal issue, and potentially applying this, activating several sprinklers at once. This has generally been used on the research base, at least, for warehouse and rack storage, and supposedly successfully, but are not being used for any parking garages. So it's not really, it hasn't been studied for that scenario, and it's a very emerging technology. So it's very cutting edge, and we don't know if this is viable or not, and obviously very expensive, and we don't know if it will work. So just an option possibly. So yeah, we're going to move to some knowledge gap points here. What is the future points we need to look at? Where should research be done to evaluate this? We have the main point being there are a few tests of not just cars, but the spread between cars. There's a lot of single car fires where somebody burned a car, usually an older one, get some data, but that tells us very little about how will the fire spread from one to the next. Fuel tank failure. We had that one test, but there's not been any further testing of what is the consequence of these fuel tanks failing and how can a fire spread from that. How effective are sprinklers? We have some testing, again, a lot of tests on one car burning. They show promise to be able to at least control the fire, but other configurations have not been tested under where there's more cars or potential larger shielded fire. What kind of response time from the fire department is required? If that is to be the sole point of putting out a fire in an open parking garage, how quickly does the fire department need to be there? This can be validated looking at statistics or just general looking at the cases, incidents, and see, and are they able to be there quick enough? Oops, I think I jumped two there, but yeah, so stacker systems, what are the risks, especially as you get up to 3 or 4 or more? We only really see tests of two stackers high. Once you get 3 or 4 cars on top of each other, is there an issue? And then generally, what is the definition of open for an open parking garage? Is, like I said, 20%. What is that based on? And changing this number, could that have an effect on the fire safety? And should that be studied further? So yeah, we've distilled this down into some proposed future research. Again, the fire spread, basically configuration of the garage and cars, and then the fuel tanks, effective nasal sprinklers, and looking at some detection and notification. Yeah, so here we have some potential options to looking at spread between several cars. Like I said, in general, just having more than one car burning, maybe 2, maybe 3, so you can see how the fire spreads to both sides at the same time. And varying the configurations, cars facing side to side, front to front, or how does the fire spread between cars in different configurations? Potentially looking at obstructions between the cars, maybe barriers. There have been some talk of having dike systems to avoid fuel leaks. How does that affect the fire? Again, the definition of open parking garages, possibly doing a test with various opening configurations of the walls around the cars, and looking at ceiling heights and especially the beam pockets and how does the smoke collect and the effects of the hot ceiling jet on spreading the fire. As the BRE test, which is shown here, found that the hot layer was very important for that preheating action of the car next to it. And like I said, the stacker system, looking at 3 or more levels, and also how a sprinkler is configured. I think in general, sprinklers are used between each car, so it's going to be a similar scenario there. But if that is not done, you can we have to look at that too. Fuel tanks. There's been some testing there generally on pool fires on different surfaces. That's the test we see here. But how does running fuel burn, and does it have the potential to spread the fire from one vehicle to the next using that mechanism? And what's the impact of the ramp that the car is parked on? If the fuel runs too quickly and spread too thinly, it can't sustain the fire, and that will be an issue. But on the flat surface, that could be different. And what is that critical angle? And what's the impact of the ignition source? Does the fuel ignite as it leaves the fuel tank? Does it spread first and then ignition occurs later? What impact does that have? And then obviously, if the fuel runs from one car to the next, is it able to rupture that tank and cause kind of a cascading effect where each tank down the line fuels the next one and ignite and rupture several vehicles in a row. Sprinklers, here's a pretty simple test of that. As I mentioned, cars in corners, we have more creative parking spot designs where they cram spots into every corner of a building to maximize the area, and that could lead to some issues when you have sprinklers put in there. The big one being effect of wind on activation. That's generally for obviously for open parking garages. If you have that 35-mile-an-hour wind, how will the sprinklers respond to that? Will the sprinklers above the car activate at all? What will the delay be? Will the delay be significant enough to cause an issue, or is not a problem? And is there a chance of activating sprinklers downwind away from the fire instead if the hot gases blow away? And if somehow the car becomes fully involved before the sprinklers activate, are they able to control the fire at all, or put it out at all? A lot of these tests are done where they ignite the car, the fire grows, and then they turn the sprinklers on, sometimes manually. But waiting to see how long can you wait and have the sprinklers still be effective could be something that should be studied. And looking at the stackers. So to look at these, can use several methods, kind of here ordered in terms of increasing cost, I would say. You can look at simple calculations of your sealing jet. You can do a statistical analysis on fires that have occurred and how have the sprinklers responded. If you have enough data on both cars and sprinklers, you can do CFD modeling, and obviously you can do the full-scale testing to look at that. And you can feed that testing data back into a CFD model to evaluate other scenarios. And then lastly, looking at the notification and response, how to improve that in some of these scenarios. What are some possible systems for an open garage environment? Is it possible to use spot detectors with all those environmental factors that can be an issue for them? And if so, what will they look like, and what will the response time be? Will the improvement in response time be enough to make a difference? If it doesn't make much sense to mandate those systems. Actually, now we have eyewitnesses, we have spot detectors and visual detectors, and if you compare all three, will you see a significant difference? And what are requirements for the fire department to respond? And should there be some standards on the garage themselves to allow larger fire vehicles to get in and have the access and be able to reach every vehicle within a certain time or something like that? And lastly, potentially looking at fighting EV fires in a cramped environment. A lot of times they do this test outside in an open space, but what if this car is parked in a dense setting, jammed in between other cars? How can the fire department get that car? How can they pull it out potentially and apply enough water to successfully put out the fire? Yeah, that's we just moving on to our thank you slide here. Thank the research panel, gave a lot of valuable feedback. We're still working on the report for this project. It should be published soon. It will be on the Research Foundation's website, free for anyone to look through. And I can basically move to questions.
Havard, thank you so much. We will be concluding at 2 p.m. today, so we will try to answer as many questions as we can. Havard and Michael, if you guys will just refer to the Q&A pod, there are some questions queued up for you there.
Yeah, there's 91, so I'm not sure I can get through all of them. Do you want to pick one here?
Just go ahead.
Should we just start at the top? There's a question about CO sensors used. I think they're used in enclosed parking garages. That's kind of all I know about that. Oops. Fuel leak. Yeah, the second question I think we kind of answered. Fuel leak in vehicles lead to ignition. It could, and that's something we think should be studied. Electric short circuits or any cable damage lead to cause fire? Yes, I believe it will, because several of the fires we discussed and I showed pictures of were specifically from electrical failures in the engine. Means of egress during fires. I think that's going to be an issue of other NFPA codes. But like I said, the safety of people is not a huge concern from the statistical point of view. I think the existing codes are pretty successful there. Fire rating for walls, that will depend on the structure. Like I said, it's generally 1 to 2 hours for most non-combustible. But like I said, you have outliers like the fire in Norway, where they only required 10 minutes, and that didn't work out so well in that scenario. But the NFPA code requires at least 1 hour, usually more. I'm reading a few here. I'm not sure if I did that question.
So yeah, this is do the 1858 fires also cover very small fires?
Oh yeah. Okay.
So I think those statistics, it all depends on what was entered into the system.
Yeah.
Certainly in the U.S. at least. Some of those 1858 fires will be small ones that stopped if they were recorded as such.
That one. I'm skipping some of these that I think we already answered throughout the presentation because we have questions from the start here. There's a question on stackers and would the entire floor be subject to extra hazard? I don't believe so, but I'm not 100% sure on that. Standards available for electric cars? I don't know. 100% EV only garages impact ventilation requirements of fire suppression. At this point, I don't believe so. The NFPA does not make a difference, and the 88A does not distinguish between EVs and gasoline vehicles. So for now, it does not. But yeah, that could be an issue if you have several EVs or only EVs in the garage. Freestanding vehicle stackers. I think the answer is no. Yeah, there are outside stacking systems or only stacking systems. I think they will just fall under NFPA 13 requirements for stackers at this point, which has, for what it's worth, has shown that with enough sprinklers, it is reasonably effective at putting out the vehicle fires. Yeah, there's a question here about the 2010 fire from the heat release rate curve. As the data shows that 2010 burns faster. I think be careful with that one is that we have very few tests, especially tests from 2010 or newer vehicles. There are not many there, kind of for obvious reason, because nobody wants to burn a 3-year-old car because it's very expensive. So whether or not that one's faster than the others, I think that could depend as much on the
scenario of how it was started.
Yeah.
It really, as far as in the talk, it's really, it's depending on where you start to fire and how you start to fire can really make a big difference in terms of the rate of heat release. So you have to take that, you have to be a little bit careful with trying to assume too much from those those heat release curves, just based on one.
Yeah. There's a ship and spare points. I believe we did a tour here as well. Did a study where they tried to establish kind of the same thing. Look, can we establish heat release rate versus year of cars, and they ran into the same issue that they had. They didn't have enough data from each decade to say anything, and what they found didn't show any reliable correlation either. So, kind of broad conclusion is that you can't really say that one decade of vehicle is larger fire or faster fire than any other. It's more about the spread. That the spread from one vehicle to another seems to be more likely with newer vehicles where we have that increased plastic content, and especially the exterior plastics. So that's kind of our broad conclusions of this report.
Our plastic gas tanks very prevalent in the U.S. Yeah, as I think Havard answered that in the it's certainly over 80% and probably growing. It's a easy way to reduce the weight of the vehicle from the much older vehicles. So that's obviously a big incentive to use the plastic gas tanks.
Yeah. Fuel tank, fuel amount remaining in the tank. Yeah, that's certainly an issue. There's a wide range of what researchers do when they burn a car. Some have emptied the tank, some have 20%, some have full tanks. So that's another thing that will heavily impact the results.
And the amount of fuel in the tank also is going to impact the spread. If you do have a leak or if the tank ruptures, how it spreads is going to be very impacted by how much fuel is in there. And that's also a very interesting, I think, issue to be looking at in the future.
Mm-hmm. It's an interesting question here. How is spread time from car to car affected by ceiling height? That's I think I would fall under one of our future research things. That's something that definitely should be studied.
But obviously, I think the shorter the ceiling height, the layer is going to form quicker and be closer to the car. So I think that's going to certainly have a significant effect.
Yeah. As a reference, there's a question about the BRE test. What's caused the shortest spread from vehicle 3 to vehicle 2? That's kind of the same vein. Is that once you have one car going, you can have 7 megawatts. You have 2 cars, you can have 16, 20 megawatts, and then the upper layer reaches 1,000 Celsius, and the re-radiation down to that third vehicle is going to be so rapid. It's going to be an exponential spread basically through these cars. And if you're an actual park garage, it's going to keep spreading. And as the fire department said, when they got to the Liverpool fire, every 30 seconds or so, another car would burst into flames just from that re-radiation and spread. Okay. Let's see another one here. Audio is spotty. Okay. Car stackers. Is there a height limitation? I can't really speak to that. I don't know.
Does the stacked one with sprinklers have sprinklers only at the ceiling? Typically, I think there's been tests with both ways, where you have a sprinkler only at the ceiling, but a lot of the testing has been done with in-rack sprinklers also.
Yeah, we got a sense that in-rack sprinklers is kind of the norm in these, so that's probably the majority of them have that setup. Another questions, battery hazards. Some of these I think we've kind of answered through the presentation. Discharge rate, I'm not sure about that. This is a long question. 1% of cases, sprinklers operated but did not extinguish a fire. It is therefore to assume that remainder were too small to activate sprinklers. Yeah, that's a lot of cases. There are sprinklers that the fire is put out before it gets big enough to activate the sprinklers. And in the cases where sprinklers operate, they seem to be effective in closed parking garages. I think we done answer this one. Not sure. Who pays usually insurance for many of these? The Liverpool and fire in Norway, the insurance companies had to pay up quite a lot. generally the insurer of the parking garage is the one paying for that. Were the UK and Norway garages sprinkler? They were not. Both cases, they were sprinklers. They were open, and they were not. There was no sprinkler or any other systems or protections there. That's certainly become up as a discussion in just a general news reporting from both of those. As should these have been sprinklered? Water mist systems, I don't know.
We haven't seen any testing on that.
No.
So water mist systems in a car fire, we have not seen that used as at least.
Possibly. I think I've seen it advertised kind of as from a manufacturer for enclosed parking garages. How that would operate if you have in a slight wind is again could be a concern, blowing the mist away. How much time would it take for a metal tank to start leaking in comparison to a plastic tank? They showed kind of similar. There were a few tests of metal tanks. They kind of build up pressure and then burst, whereas the plastic tank starts to drip. But again,
that was usually like 4 minutes, right?
Yeah.
So they're usually at the longer end of the plastic tank. Sprinkling or leaking, excuse me.
Yeah, and again, there aren't really any metal tanks left, so it's kind of they aren't being used anyway. So we're gonna have to look at the plastic tanks and how do they perform.
On behalf of the National Fire Protection Association, the Fire Protection Research Foundation, Havard, Michael, and myself, thank you for joining us today.